Hello there, friends and neighbors. I'm going to show you how to compute a one-way ANOVA, that is analysis of variance, with Excel without any special packages uploaded or installed. First, we need to pull up a data set. So I've got a data set open, and it has 3 different times of day. And for each of them, we've got the count of the number of people who come out of the bathroom in Centralia College at that time of day. We've got morning, noon, and afternoon, 3 different times of day, and the count for each. We want to test HO. All mu's, that is population means, are equal for the 3 times of day. Okay. Against H1, at least one pair of mu's is different from each other. Okay, that is, morning is different from noon, or morning is different from afternoon, or noon is different from afternoon in terms of the population mean. Then we have to pick an alpha, and that'll be, oh, I don't know, 0.05 will be all right. Okay, we're going to create an ANOVA summary table, and that looks like this. Source, and the sources are going to be between groups variation, which is also called the treatment effect. It's also called the numerator. It's also called the factor. Okay, and we've got within groups effect, which is also known as error, also known as the residual. And then finally, we've got total. And for each of these sources, we've got the degrees of freedom and the sum of squares. And then we'll combine the degrees of freedom and the sum of squares to the new variance term, which is called the mean square. Then I'll take a ratio of those 2 variance terms, those 2 mean squares, to create the F, which is our test statistic, and the p-value will be the last thing we get. So if we're going to be computing means, then certainly we will need to start by computing the mean for each group. So that is x bar, the group mean. And that equals average for each group. So I'm going to get the average of the mornings, I'm going to get the average of the noons, the average of the afternoons. And in each case, just copy it and paste it as text, so that every individual in the morning group has got the same group mean. It's 23.4. Everybody in the noon group has got the same group mean, and everybody in the afternoon group has got the same group mean. Okay, then we need the grand mean, which is x bar bar. I'll just say GM. That's the mean of everybody. So that's the mean of all the observations. It's 19.1. Everybody has the same. Now we start computing the squared deviations. So for this, we'll have between groups variation and within groups. Squared deviation, residual, I guess we could go, well, I'll call it deviation. And then we've got within groups deviation. And of course, we're talking about squared deviations. We can also get the total deviation just for fun. All right, between groups deviation, open parenth, that would be each x bar minus the grand mean. So that is the deviation of each sample mean from the group, from the overall grand mean, which we square, of course. And we do that for everybody. And you'll notice we have the same deviation for every member of the morning group, the same squared deviation for every member of the noon group, and the same squared deviation for every afternoon. And within groups variation is the deviation of each individual from their group mean. And for this, every person in the data set will have a different value. And just for fun, we'll compute the total deviation equals each individual value minus the grand mean. I'm just doing this for fun. Squaring it. We don't strictly need it, but I'm going to use it to show you how this is a true additive partition. Now the degrees of freedom between groups is equal to the number of groups minus 1. So that's k minus 1. K is equal to 3. Okay. Within groups, variation is n minus k. Okay, that is total sample size minus the k groups. And then the total degrees of freedom is n minus 1. You'll notice that n minus 1 can be divided, additively partitioned into n minus k plus k minus 1. The k's cancel out, and we end up getting n minus 1. So n, because there are 20 individuals, n minus 1 should be 19. And n minus k, with 3 groups and 20 individuals, is 20 minus 3, 17. And k minus 1, 3 minus 1 is 2. You'll notice that 17 plus 2 equals 19. Now to get the sum of squared deviations between groups, I'm going to sum this, just like it sounds. Sum of squared deviations. Here are the squared deviations between groups, added up. There it is. From that, I'm going to compute the variance between groups, also known as the mean square between groups, the treatment effect, equals, as with all variances, the mean square is the sum of squares divided by its degrees of freedom. And there it is, 204.9. Is that big? Well, I have no way to know whether it's big or not. I need to have context. And that's what the within groups variation will give me. So I'm going to compute the sum of squares within group equals sum of squares within group. There it is. From that, I'm going to compute the variance within group, which is the mean square. That's equal to the 939.98 divided by 17 degrees of freedom. Sum of squares over degrees of freedom. That's the definition of any variance, including mean squared. And there we go. Before we move on, I want to show you that this is a true additive partition. Okay, so I'm going to sum the total squared deviation. Okay, and there it is, 1349.8 equals 939 plus 409. And you'll notice that this literally adds up. It's a literal additive partition. If I wanted, I can compute the total variance equals the sum of squares over the degrees of freedom. And that would give me the same result I would get if I used equals VAR, the variance of the individual values. Notice it's the same exact number. Also notice that the variance, the mean square, is not an additive partition. If I were to add these two numbers together, the between group and within group mean squares, I would get something different from 71. Okay, and you see I get 260, very different from 71. Okay, and that's why an ANOVA summary table does not report the variance, total variance. It just reports if it reports anything at all, very often it won't. But if it does, it only reports the sum of squares and degrees of freedom. Now the last two steps need to compute the F and the p-value, which will permit me to make my decision. So the F is a ratio of mean squares between groups divided by mean squares within groups. In other words, treatment effect divided by error equals mean square between divided by mean square within, enter, 3.71. This finally permits me to determine if this is a large factor effect. That is, if the means are far apart. I say compared to what, and what I'm comparing it to is within group variation. So the last step is to get my p-value. Since this is an F-test statistic, that means I'm going to use the F distribution, equals F-dist. Open parenthesis, choose the F, choose the degrees of freedom treatment, and then choose the degrees of freedom error. Close the parenthesis and hit enter. Now the p-value is 0.046. Here's what that formula is. Treatment, DF error. And that's how we do it. Well, that p-value is statistically significant because it is smaller than 0.05, and so I reject the null hypothesis. And I conclude at least one pair of means is significantly different from 0. Okay? I'll say significantly different from each other. Well, I don't know which pair it is. I've got 3 possible pairwise comparisons: morning to noon, morning to afternoon, and noon to afternoon. I have no way to figure out which one is which. And that's what the next step is for. That's a follow-up comparison, which is a bunch of pairwise t-tests, which is a little bit too advanced to do in Excel. If you want to do that, and you should, you need to use appropriate software, such as R or SPSS or SAS or whatever software you've got. Okay.